today, which is lecture 10, which is sort of related to what we've been talking so far with electric fields, but sort of different in that it's a new topic. And now we'll start to look at magnetic fields. The whole idea is just like what we did with direct current or DC circuits, right? We started with electric fields and sort of developed the concept of current and voltage and then analyzed direct current circuits. So similarly in this module, if you'd want to think of it that way, we'll start with magnetic fields, magnetic forces, and sort of develop that into alternating currents or AC, and then look at AC circuits and analyze AC circuits. So that's sort of what we'll do in this next 3 weeks of the course. Yeah, so let's start with magnetic fields, and we will borrow a lot of concepts, a lot of tricks and strategies from what we've learned when we talked about electric fields. There will be a lot of parallelism. And so that's why I sort of went slowly with electric fields, but we will just borrow those concepts. We will use the skill of the cross products. We encountered this when we learned about angular momentum in 124, 104. I'm aware some people haven't done 104, so I will go through the cross products, finding the directions, particularly if you have two vectors that are being crossed, what's the direction of the third cross product. All right, so the first parallelism is the generation of magnetic fields. So when we talked about electric fields, we learned that if you have a charge, that charge will create an electric field around itself, right? So charge equals electric field. Now, if you have a magnet, then that magnet will create a magnetic field around itself. Yeah, so magnetic fields, they're created by magnets. And the unit we will use for the magnetic field is the Tesla. You will find other units for magnetic fields like the Gauss. That's a non-SI unit. Here's the conversion factor you need to convert from Gauss to Tesla, but largely we will use the unit Tesla. So just like electric fields are set up by charges, magnetic fields are set up by magnets. Magnets, they always have a north pole and a south pole. So we cannot separate the north pole and south pole of a magnet, even if the magnet is very tiny or small. There are some research focus on finding a monopole, like a south pole or north pole existing by itself, but after decades of research, that's yet to be found. So to date, we are still using, the magnets always have a north pole and a south pole. And just like opposite charges repel each other and like charges attract each other, in terms of magnets, we are talking about the poles, the north pole and the south pole, so that like poles repel. Okay, north pole will repel a north pole, whereas opposite poles attract, as you can see here, a north pole attracts south pole. Okay. A magnetic field is also invisible, but we know that if you have a magnet and you put iron filings around that magnet, the iron filings sort of arrange themselves, and we see this sort of arrangement here. And so we use this arrangement to come up with a way to visualize magnetic fields, right? Just like electric fields being invisible, we came up with electric fields to sort of enable us to draw electric fields via electric field lines. We will also use magnetic field lines to draw the magnetic fields. So we draw the magnetic field lines as closed loops. Okay. They always form closed loops. Unlike, electric field lines, you have a positive charge and a negative charge. The electric field sort of originates from the positive charge and terminates at the negative charge. But for magnetic field lines, the magnetic field lines are continuous. They form closed loops even inside the magnet. the magnetic field lines are continuous, and that's a consequence of poles existing in pairs all the time, right? You always have a north pole and a south pole. The magnetic field lines also tell you how strong the magnetic field is, so that the denser the magnetic field lines are, the stronger the magnetic field in that area is. Okay. And of course, because we use magnetic field lines to visualize magnetic fields, the magnetic field lines tell us the direction of the magnetic field. In terms of direction of the magnetic field, as you know, as we might observe, as I've mentioned earlier, if you have a magnet and put iron filings around that magnet, the iron filings will arrange themselves. But of course, the iron filings, they don't have arrows, right? So by looking at the iron filings, we just see that the iron filings arrange themselves, but the iron filings itself do not tell us that the magnetic field lines go from the North Pole to the South Pole. It doesn't have like these arrows here. But by convention, we adopt the direction that the magnetic field lines come out of the North Pole. Right? Notice the direction of the magnetic field lines here. The magnetic field lines come out of the North Pole, and the magnetic field lines enter the South Pole. So that's the convention that we use, and just keep this convention in mind, because when we talk about how currents generate magnetic fields and how magnetic fields generate currents, the direction of the magnetic field is important. So we will now set up this convention where, you know, if you have a magnet will always have a North Pole and a South Pole. If you draw the magnetic field lines, the magnetic field line should come out of the North Pole. Of course, it will form a closed loop, but it will enter the South Pole of the magnet. The magnetic field line will continue inside the magnet, so that you have this closed loop right here. All right. Now I'll show you a demonstration. It's quite a big demonstration, so I couldn't bring the equipment to here. Let's see how. And I think I have to transfer to. Just to pause. Okay, so since the magnet, of course, the magnet will generate a magnetic field around itself, as we've been talking about. And when you bring the magnets with the magnetic field close to the electron beam, the electrons bend. So that's a demonstration that the electrons, being charged particles, when they are moving in the region of a magnetic field, they experience a magnetic force, right? And the magnetic force that the moving electrons, moving charges experience is what caused the electron beam to bend. It's the presence of those two things. You have a magnetic field exerting a force on a moving charge. Okay, that creates the magnetic force. So mathematically, we can represent that observation as being, if you have a charge Q that is moving with a velocity v in a region of magnetic field B, then that charge will experience a force F. And that force is, of course, the magnetic force that it experiences. So analyzing this mathematical equation, we have three vectors. So the force is a vector, velocity and magnetic field, these are vectors, and this one is the cross product between the vectors velocity v and magnetic field b. So what that tells us is if you're getting the cross product of two vectors, then the result will also be a vector, which in fact is force, which we know is a vector. So the way to work this equation out is first get the magnitude of the force. You can calculate the magnitude of the force by expanding the definition of the cross product. The cross product is defined by a sine theta function. So the force is therefore equal to Q times V. V now is the speed, the scalar counterpart of velocity, times the magnetic field magnitude and the sine theta, where theta is the angle between the two vectors that are being crossed. Right. So by defining the cross product as a sine theta function, that allows us to calculate the magnitude of the magnetic force that the moving charge experiences. And it also tells us that you will only experience, the charge will only experience a force if it's moving, it has some speed v, if it's stationary, or if the charge is moving parallel to the magnetic field such that theta is equal to 0, right? Parallel movement means V is parallel to B, hence the force is equal to 0, right? So writing it in terms of a cross product sort of gives us this important physical implication that the charge will only experience a force if it's moving, and if it's moving such that it's not parallel to the magnetic field. Right, so that's how you calculate the magnitude. Of course, force is a vector, so you need to determine its direction as well. To find the direction, you have to use the right-hand rule. So you have these two vectors, the velocity and the magnetic field vector. You need to do right-hand rule. Okay, a revision of the right-hand rule. You can either use your, that's why it's called right-hand rule. You use your right hand. Okay, so we have three methods to use the right hand. It's always the first vector, V. So the order of the vectors is important. It's always the first vector, velocity, being crossed with the second vector, the magnetic field. So in the first method, the curling method, you point your forefingers in the direction of the velocity vector and you curl your forefingers in the direction of the magnetic field. Right, so velocity is upwards, magnetic field is to the left. Curling it here, and the thumb will point to the direction of the force. In the second method, which I call the slap method, the thumb points in the direction of the first vector, the velocity vector. Four fingers point in the direction of the magnetic field vector, which is the second vector in your cross product equation, and you slap your hand in the direction of the force. All consistent. And the third right-hand rule method is using your three fingers to form the XYZ axis, perpendicular, all perpendicular to each other. The thumb is pointing in the direction of the velocity vector. Your forefinger points in the direction of the magnetic field, and your middle finger points in the direction of the force. Right? Okay, so you can use any of these three methods. They should all be consistent and give you the same results. But if you're like me and you don't want to twist your hand and use your fingers, you can use the fourth method, which uses the three coordinate axis X, Y, Z, right? Just a quick refresh. We represent the positive X as a plus I hat vector, the plus Y as a plus J hat vector, and the plus Z axis as the plus K hat vector. So of course, you also have the minus I hat or minus X direction, minus J hat or minus Y direction, and the minus K hat or the minus Z direction, all perpendicular to each other. And so if you use this coordinate system and if you do the cross product, the cross product always involves two vectors, and the answer will be the third vector that's not involved in the cross product. So say, for example, here you do I hat cross J hat. Okay, so you're using these two vectors, I hat, you're crossing I hat over to j hat. So the answer here will automatically be k hat. And then you're just left to determine whether that's a plus k hat or a minus k hat. And you determine that by looking at whether you crossed in the clockwise or the anti-clockwise direction. If you crossed in the clockwise direction, then you have a negative sign. If you cross in the anti-clockwise direction, you have a positive sign. Right? So in this particular example, I hat cross j hat, you're going from I hat, you're crossing that onto j hat, you're going in the anti-clockwise direction. Right? Hence, that should be a plus k hat for the answer. And you can verify that with your right hand rule. K hat, that will be the direction that's pointing out of the page, right? Out of the board or out of the page, out of the plane. Minus k hat, that will be pointing into the page, right? And it's such that if you do, for example, let's take an example of a clockwise cross product. If you're doing I hat crossed with k hat, automatically your answer will be j hat because it's the only vector that's not involved in the cross product. But you're crossing I hat onto k hat in the clockwise direction, so that will be a minus j hat for the answer. Cool, right? Is it all coming back from semester one? I hope that's clear enough. So let's do a little bit of practice. So you have here some charges. They're either positive or negative charges. They enter a region with magnetic fields. Magnetic fields represented by B. Each of the magnetic fields have directions indicated, like B in means the magnetic field is into the page. So an X shows you an arrow that's pointing into the page, and you're looking at the arrow tail. And that's why that's represented by an X there into the page, or upwards, of course, just an arrow pointing upwards. So for each of these scenarios, try to determine what's the direction of the magnetic force. All right, the first one, the magnetic force is upwards. Remember the magnetic force is QV cross B. So you're doing first the direction of the velocity, and you're crossing that to the direction of the magnetic field. So here, the direction of the velocity is I hat plus I hat. You're crossing that onto the minus k hat. Right, crossing that onto minus k hat, the answer will be j hat. That's the only vector that's not involved. But when you do the cross product, you're crossing in the anti-clockwise direction. Hence, that's a plus j hat, which is upwards. Right. Okay, for this second example, right, you have a minus I hat. You're crossing that to a plus j hat. Okay, so of course, the answer will be k hat. When you do the cross, you're going in the clockwise direction, so that will be so that will be a minus k hat because you're going in the clockwise direction. But notice that's a minus charge. So a minus charge, right? The effect of the minus charge is you have a minus k hat. So the minus k hat here comes from the cross product of I hat cross to j hat, giving you a minus k hat, but the charge is negative. So the negative charge will reverse the direction that you got from the cross product. So you also have to consider the charge, whether it's positive or negative in your final answer. And hence, the final answer is a plus k hat, which is out of the page. Good. Right, how about the third one? What's the magnetic force here? Or the direction? Or is there a magnetic force? No, yeah, it's a cross product, right? You'll only have a force if you're crossing two perpendicular vectors, but here, right, they are anti-parallel, so there's no force or no deflection. And if you have a diagonal vector right here, remember that a diagonal vector can always be broken down into horizontal and vertical components. So you have the X and Y components of your magnetic field vector. The Y component is parallel to the velocity vector, hence the Y component will not contribute to the force. And all you have to do is get the cross product between the velocity vector, which is a plus j hat, cross that with the X component of the magnetic field vector I hat, right? You're going in the clockwise direction, so that will give you a minus k hats into the page. Good. All right, are we happy with finding directions for the cross products? Yeah. All right, so here now, for example, so we won't go through this exercise in detail because we just did the example there, but the exercise is here to demonstrate something. So for example, you have these four charges, they're positively charged and they are moving in different directions. One is to the right, upwards, to the left, and downwards. If you work out the direction of the magnetic force, so say here for charge A, yeah, we already know the direction of the magnetic force will be V, which is I hat, I hat crossed with the magnetic field direction minus K hat, right? So you're doing a I hat crossed with minus K hat. Well, you know that the answer will be J hat and you're crossing in the anti-clockwise direction. So that's a plus J hat, meaning you'll have a force that's pointing upwards. If you do the same exercise for charge B, charge C, and charge D, you will find out that you will have a magnetic force. Right. If you do that exercise, you'll find out that the magnetic force will be pointing towards some central point. And is it reminding you of something that you learned from semester 1 from mechanics? Right. Okay, if you have a force that's pointing into something like a central point, okay, then what can we say about this charge? It's sort of, yeah. Well, let's look at this demonstration to see.
What we're here to do.
Yeah, I need to transfer to the, because the sound is. Right. So you sort of have the, it forms this circular path here. So we can relate the magnetic force, okay, this force that the charge, the moving charge experiences is because of the magnetic field that it's in. So this force here is the magnetic force that the moving charge experiences. And then we can relate that magnetic force to the circular motion that the moving charge experiences. So a little bit of a refresher, right? The fact that you have acceleration because the direction of the motion of the charge changes means that there has to be a force acting on that charge that's accelerating. And according to Newton's second law of motion, force is equal to mass times acceleration. The acceleration is called centripetal acceleration because the acceleration is always directed towards the center of that circular path. right? And centripetal acceleration is defined as v squared over r, okay? The tangential speed squared or linear speed squared divided by r. And of course, you need to have this centripetal force, Fc, that is causing your centripetal acceleration. So this Fc equals mv squared over r. It's just coming from Newton's second law of motion, right? F is the centripetal force, m, that's just carried over as m, and then a is the centripetal acceleration, v squared over r. So v squared over r here is the centripetal acceleration. Now, this is for any object that's moving in circular motion, right? For our particular application, we have a charge that's moving in a circular motion because of the magnetic field, right? It's the magnetic field that provides this centripetal force in order to cause the charge to move in a circular motion. Hence, if we write down the Newton's second law of motion for this charge, we will use the magnetic force provided by the magnetic field, right? So the magnetic force, of course, we saw that mathematically as a vector, QV cross B, but we expanded that. We said we can use the sine theta function to remove the cross product. Sine theta will be equal to 1 because the velocity is perpendicular to the magnetic field, right? I hat is perpendicular to k negative k hat. Hence, the magnetic force is just equal to QVB. Right. We can then use this magnetic force. It's this magnetic force that provides the centripetal force. Hence, you have the centripetal force is equal to QVB, right? So this is centripetal force Fc, which is provided by the magnetic force QVB, and mv squared over r is carried over from there. Okay. We're talking about the same charge undergoing the circular motion. So this speed v is the same as this speed v, that cancels each other out. And hence you have this relationship, which you can then rearrange to find the speed of that charge in the magnetic field region. Right, so if you want to determine the speed of this charge, it all comes from the relationship of centripetal force being provided by the magnetic force QVB, and that's equal to mv squared over r. Okay. And this is a pretty general observation that for any charge that moves in a uniform magnetic field, the charge will undergo uniform circular motion. And by using this fact, we have a device or an equipment called the mass spectrometer. So the mass spectrometer, it's an equipment that determines the composition of a material, right? It's very much used, for example, in astronomy, where you bring home some material from Mars or the moon, and you analyze what are the elements, to determine what's the composition of a moon rock, for example, or a meteor, or any unknown material. It's also used in food technology to determine what is the composition of a food product. So the way a mass spectrometer works is that you have an unknown substance. You don't know which species, you don't know which elements make up this substance, but by accelerating, by making that unknown species move with a known speed in the magnetic field region. So you have here the magnetic field, the X's represent the magnetic fields. They're pointing into the page. You have a uniform magnetic field, but as indicated by the uniform distribution of the magnetic field lines, right? You have this uniform magnetic region here. And then you have the unknown ions, unknown species They enter this uniform magnetic field with a known speed, right? Speed v. And as we've seen in the previous slides, if you have a moving charge in a uniform magnetic field, this moving charge with some speed v is deflected so that it undergoes uniform circular motion in the magnetic field region. So the dashed line here traces out the uniform circular motion path that the charged particle takes. But then you put a detector midway so that the charged particle really just forms a semicircle. But by putting a detector in the path of the charged particle, you can measure the radius. You can measure the radius of the circular path of the charged particle. And we've derived this equation from here, right? By relating the magnetic force that the particle experiences and measuring the, we know the speeds, we can measure the radius, right? By using this relationship here, we are able to determine the mass. Okay. Right. So the magnetic field, we know that because it's what we apply. And the charge, it's an electron or a proton, so we know the charge. The speeds, it's one of the parameters. We have to know the speed of the particle, and the radius, we measure the radius of the circular path of the particle that undergoes circular motion in the uniform magnetic field region. So by knowing these parameters, we are able to calculate the mass, right? And each species has a known mass, right? If just look at the periodic table and see what's the mass of carbon, for example, if it matches the mass that you've calculated from the mass spectrometer, then you know that there's carbon in that unknown material. Okay. Right. So the really crucial thing is you have to know what is the speed of the particle that enters this uniform magnetic field region. The problem is, how are you going to know the speed of that particle? You will know the speed of the particle by using this part of the equipment, which is called the velocity selector. Right, so it's from the name velocity selector, it means it selects the particles with a particular velocity. So let's look at the velocity selector and how it operates and how it's able to select particles based on their velocity. So the purpose is to allow particles with some known velocity to move through this velocity selector undeflected. Okay. So the goal is that if you have a particle, the particle should pass through the velocity velocity selector straight through, undeflected, so that it just goes straight through and then it reaches the uniform magnetic field region of the mass spectrometer. How do you do that? The velocity selector needs to have an electric field and a magnetic field, because we know that if you have an electric field, that electric field will apply an electric force onto the charge. And if you have a magnetic field, the magnetic field will apply a magnetic force onto that moving charge. And if the magnetic force and the electric force balances each other out, then you have a zero equivalent force. You have a zero net force acting on your moving charge. Zero net force means your charge just passes through undeflected. So any charge with that prescribed speed that balances out the electric force and magnetic force will pass straight through, but any other charge with a different speed will be deflected towards the plates. Okay. And they won't reach the mass spectrometer. They won't contribute to the uniform circular motion later on. Okay. Does the concept make sense? So, yeah. at least the concepts, right? Because then we will go to the maths of how we select the material. Okay, and this is probably one of the most important applications of the combination of electric fields and magnetic fields. So you can be sure that it will be it will be tested, because it's sort of combining now the knowledge of electric fields and magnetic fields. Right. So are we okay with the concept there? Yeah, all we want is to balance out the electric force. So you have an electric force there because of the magnetic, sorry. Yeah, we have an electric force because of the electric fields. We have a magnetic force because of the magnetic field, right? The combined forces, right, will just be the sum of the individual forces. The electric force is charge times electric field, as we learned before. And then for the magnetic force, QV cross B. Right? So the total force, you can expand this as, you can also write it as electric force plus magnetic force. Okay. And the combined forces is what is called Lorentz force equation. But then the idea is that the electric force should balance out the magnetic force so that the net force is equal to 0, right? If the net force is equal to 0, okay, that means the electric force is equal to the magnetic force, right? In terms of, yeah, the negative sign just tells you that the directions need to be opposites, right? As you see here, the direction of the electric force is opposite the direction of the magnetic force. If the magnitudes are equal, then these two forces should cancel each other out. So effectively, your moving charge will experience 0 net force, and your moving charge will just pass through the velocity selector straight through without being deflected. Okay. Right. But by balancing out the forces, we can see, it's the same charge that's moving through the fields. And therefore, any charge that has a speed equal to the ratio of the electric field to the magnetic field will pass straight through. And any charge whose speed is anything except this ratio will either be deflected to the positive plate or to the negative plate of the velocity selector. Okay. This one, V is equal to E over B. The charge will just pass straight through. Any other speeds, the charge, if it's a positive charge, of course, it will be attracted to the negative plates of the selector. If it's a negative charge, of course, it will be attracted to the plate of the positive plate of the selector. Good. Does that make sense? Like the concept of it? Okay, so let's assume any particle that has a speed of E over B then reaches the mass spectrometer with uniform magnetic field. So let's assume this is the charge that got through the ratio E over B. Okay, so say here you have this charge that passes, that enters this uniform magnetic field region, right? Which point charge here is heaviest and positively charged? It's now in the mass spectrometer region, right? You have selected the correct velocity of the particle. Any particle whose speed is E over B will reach this uniform magnetic field region. Okay, we learned that that particle will undergo circular motion, right? Which particle will be positively charged and heaviest? Yeah. Just a reminder. Your charge will experience this magnetic field region. It will feel the magnetic force QV cross B. Right. For direction, remember to use the right-hand rule. Okay. And for magnitude, use QVB, and of course, centripetal force is mv squared over r. Any voluntary answers? So 25% chance of getting the right answer, yeah? Hey, the answer is A. Right? You can first try and work out the direction to sort of try and see roughly where it should be deflected. So for the direction of the magnetic force, right? You have there, the velocity is pointing upwards. So you have a J hat. And the magnetic field is into the page. So, so that will be a J hat crossed with negative K hat. Of course, it will give you I hat, but then you're doing J hat crossed with negative K hat, right? You're doing a clockwise cross. So that means that's a negative I hat for the direction. So it's either, so your charged particle will then be deflected to the left, right? So it's either particle A or particle B, right? Because it's positively charged. So particle A and particle B, they're both positively charged, but which one will be heaviest? Heaviest meaning biggest mass, right? So mass comes into the centripetal force equation there. Good, yeah? So centripetal force is mv squared over r. The centripetal force is provided by the magnetic force, QVB. Hence, right, V will cancel each other out. The mass, mass is equal to QRB over V, which tells you that the mass is directly proportional to the radius. Yeah. So the bigger the radius of the circular path is, the bigger the mass. Okay. And when we're saying radius, we're talking about this. Yeah, this is radius. It's not this. This is not the radius. This is actually the diameter of your circular path. This is the radius, half of the diameter. So similarly for this one, the radius should be from the circle center. Yeah. And that's why A will be the heaviest because it's deflected with a bigger radius. It forms a bigger circular path compared to particle B. Good. Any question about the concepts we've learned or this exercise, particularly the mass spectrometer and velocity selector? Okay. Right, we will look at a numerical example of the velocity selector and the mass spectrometer in the beginning of the next lecture. So if you don't have any question, I'll end the lecture here and I'll see you in the next lecture tomorrow, where we will still talk about magnetic